Okay, now we're going to be we just got done with exponential models, and now we're going to be putting those together with our linear models. So our objective for today is going to be choosing between linear and exponential models for a given data set, and then we're also going to be writing those models. Okay, so in this first task here, we have two venues or locations are possible meeting places for a yearly convention. Each venue projects a different pattern for the expected attendance at the yearly convention for an 8-year period. So we first want to look at these and ask which venue projects a common difference of attendees. So a common difference would be that subtraction. Okay. And if there is a common difference, then that gives us a heads up that it's going to be a linear relationship. And that common difference we refer to usually as it's that slope, right? How much does it go up or down each time? So we're going to go ahead and we're going to analyze these two. So we have the two venues. Okay. And we want to look to see, do they go up by the same amount each time? So we're going to go ahead and do some subtracting. So if we can grab a calculator, if we want to here, for this first venue, so I'm going to take 2650 and subtract the 2500. Oh, the difference of that is 150. What about the next one? Is that difference also 150? It is. What about the next one? Yep, and we can keep going. Minus 2950. And it looks like, well, it's nice that first venue has a common difference because when I subtract these two, it goes up by 150 each time. So they show the attendance going up by 150 every year for each year. And it's important to note this also goes up by the same difference. This also goes up by 1. If this over here didn't go up by by the same amount each time, this common difference would be meaningless. Okay, so they both go up by that same difference. So, well, that kind of answers that question. Let's double check the second one to see, does that one go up by the same amount each time? If we take 1250 minus 1100, that's up by 150. And the next one, nope, that's 170. 194. Nope, that next one is not a common difference. So which venue projects? Venue number 1. So venue 1, a common difference of 150. So that tells me that for every, and then so that kind of helps me there with that slope a bit. So for every one my rise, it goes up $150 per every 1 year. So the slope is in, not dollars, people. We're talking people here. 150 people per year. So this is our rate of change. If you remember from our linear equations, our rate of change is 150 people per 1 year. That's the rate at which the population or the attendance is changing. It's going up by 150 people per year. So which venue projects a fixed percent change? So that fixed percent change would indicate an exponential function, an exponential relationship. And there, instead of looking at a common difference, like here for venue 1, we're looking for a common ratio. So instead of a common difference, we're looking for a common ratio, which ratio involves dividing. Okay, so we're looking for that common ratio. So let's go ahead and let's do some dividing here. Let's bring up my calculator again. And we know it's not venue 1. And if I did the division for venue 1, 2650 divided by 2500, 1.06, 2800 divided by 2650, 1.056, 2950 divided by 2800. If you note 1053, it's not the same. It doesn't have that common ratio. Whereas this one, 1250 divided by 1100, gives me 1.13. 1420 divided by 1250, 1.136, and the other one was 1.136 as well. 1614 divided by 1420, 1.1366. 1834 divided by 1614, 1.136. So it looks like it's pretty consistent in 1.136. So to go from here to here, I multiply by 1.136. To go from here to here, I multiply by 1.136. So forth and so on, multiply by 1.136. So it has that common ratio. So venue 2 has a common ratio of 1.136, which then I can get, so this is a exponential growth function with a growth rate of 1.136 minus 1, which is 0.136, which would be 13.6%. So instead of it growing linearly, like in this case, venue 2 is saying it's going to grow exponentially. Okay. So we want to graph each set of data. What type of function does each graph represent? Okay, so if I was to graph them, we already talked about what type of function. We already did this. What type of function does each graph represent? And if I graph those first ones, let's go ahead and let's graph those using our graphing calculator. So I bring up my graphing calculator again, and I want to graph those points. So to do that, I hit, again, that stat button, edit, and we want the point 0 through 7. I have 5 already, so we just need to add 6 and 7. Okay, and then over here, let's plug those points in. 2,500, 2,650. If you notice, my calculator doesn't show the whole thing just because it's kind of squished. 2,950, 3,100, 3,250, 3,400, 3,550. Okay, now if I go to graph, first of all, I haven't told my calculator to graph it. I have to go to second y equals stat plot and turn them on. Enter. Now my x's are in list 1, my y's are in list 2, so now we go graph. It says they're on. Do you see where it says plots, x and y? Why can't I see them? Well, look at these points, you guys. These are all up in the thousands. If you notice over here, I'm only seeing up to 800. According to my graph, you're probably seeing something different. So I need to change my window. My x's need to go from about 0 to 7. So go to my window. Let's go to my x's. We can keep that from -2 to 10. That would hit my 0. 0 to 7's in that window. But look at my y's. My y win is 200 right there, and my y max is 800. I need to see way farther than that. I need to see from about 2,000, let's add another 0, up to 3,550. So let's go 4,000. And for my y scale, this is, what am I counting by? Am I counting by 50s? Let's count by 100. Let's go ahead and graph them. There's my points. And if you can tell, if I was to connect the dots here, this makes a very straight line. A straight line with a slope of 150, up 150 over 1. Okay? So it makes a very straight line. And so we can actually write an equation for that straight line. And we're going to do that. This doesn't ask me to do that, but we're going to do that. So we want to write a linear equation. To write a linear equation, y minus y1 equals mx minus x1. I need an ordered pair. I need an x1, y1. Well, we have tons of them down here. Pick one. I'm going to pick the easiest one, which is the 0, 2,500. So x is 0. My y is 2,500. So we'd have y minus 2,500 equals slope. What is my slope? Rise over run, which would be change in y over change in x. We know here my change in y, it goes up by 150 each time. My change in x over here goes up by 1. So my slope is 150 over 1, x minus 0. So we can simplify this guy out a bit. X minus 0 is just x. I'm going to add the 2,500 to both sides. So my equation for this first venue equals y equals, let's put on here, y equals 150x plus 2500. Or in other words, this is my y-intercept, which we could tell from the graph. It's that point right there, and my slope is 150. So I can come into my y equals, and I can graph this, 150x plus 2500, and graph it. Looky there, it hits every single one of those points. And now I can use this to make predictions. What do I think the population, how many people are going to attend this event in 15 years? I can type in a 15, 4,750 people for my Y1. Or I could plug a 15 into here. I can plug a 15 into here, 150 times 15 plus 2,500, and see what I get. Or year 20 or year 30, or how many people at each year. Okay. All right, the next one, venue 2, is an exponential. So we need an exponential function, y equals a times, sorry, Siri decided to pipe in, a times b to the x. Well, a comes from our very first, so I can tell my a, they give me that 0 is 1100. So my a is 1100. And I know the b is that growth factor. And I know I'm multiplying by 1.136 each time. So 1.136 to the x. So there's my function. So let's go ahead and let's look at both of these on my calculator. Okay, so I need to come to my stat, and I need to edit, and I need to change these numbers because these are different. So let's go ahead, let's change those. It's 1100, 1250, 1420, 1614, 1834, 2084, 2369, and then 2692. Okay, so now let's go and let's clear out my y equals. My plots are on, which is awesome. We want them on. But I'm not seeing far enough down because this one actually starts over here. This one goes as low as 1100. This one here started at 2500. So we're going to have to adjust my window. My y only sees down to 2000. We need to see down to 1000. So let's go ahead and do 1000, and let's look. There's my window. And if you can see, this has a slightly curvier look to it, which kind of indicates that exponential. So we can actually graph it. It's 1100 times, it was 1.136 to the x. And looky there, it hits every single one of those points. Okay, so there's our exponential model.